All right, welcome back, everyone. Today we'll talk about three things. So we have so far talked about multivariate statistics, and now we'll talk about three things based on multivariate statistics. The first one is multivariate hypothesis testing, and then we'll talk about two different control charts. The first one is when mean and covariance are known, and the second one when mean and covariance are unknown. Okay. All right, so the first thing is hypothesis testing. It's very much like a regular hypothesis testing, except now you have multiple quality characteristics. So you basically have a mean vector. So you're not comparing a number to a number, you're now comparing a vector to a vector. So essentially, in my notation, this is mu underbar equals to mu underbar 0. And then alternate hypothesis is mu underbar not equals to mu underbar 0. Okay, so how do we do this? Let's write down the steps before we look at the example. The first one is compute a test statistic, right? Which is basically your test statistic that you computed in your regular hypothesis testing as well. This time, it's actually called Hotelling t-square statistic. Okay, one thing that you need to keep in mind is anything that we do in, or anything that you do in multivariate statistics, you will always compute a Hotelling t-square statistic, always. But the formula for Hotelling t-square statistics will keep on changing. It's not like univariate where you have a t statistic, z statistic, f statistic. No, in this case, you always have a t-square statistic. It's just that the formula for t-square will change depending on the scenario. Okay, so right now for multivariate hypothesis testing, your t-square is m times x over bar under bar minus mu under bar, mu 0 under bar transpose S inverse x over bar under bar minus mu 0 under bar. And then this m is your number of samples. Okay, and we already know mu under bar 0, x over bar under bar. Those are your mean vector and sample average vector. Okay, so you have computed the test statistic. Step number 2 is now you compute the critical value. Your critical value is t-square critical alpha. This is equal to m minus 1 divided by m minus p times f of alpha. This is your f statistic, p comma m minus p. The numerator degrees of freedom is p. The numerator degrees of freedom is m minus p. And this is your f statistic. And p is always, this is the number of quality characteristics or the dimension of the problem. And then the last step number 3 is if t square is greater than t square critical at level alpha, then you reject H naught. Okay. And that's pretty much it. That's what we'll do in hypothesis testing. So let's look at an example here. The question says, doctors were studying health indicators for a person. The subject under study is perspiration and its content. Aiming to establish a normal baseline for healthy persons, perspiration from 20 healthy females were collected and analyzed. 3 components, X1, sweat rate, X2, sodium content, X3, potassium content were measured. The result, which doctors call sweat data, are presented in the following table. Okay, so you see here, you have 20 healthy females. So number of samples is 20. And you have 3 quality characteristics. So P is 3. P is 3. And we can say our quality characteristic X is composed of X1 sweat rate, X2 sodium content, X3 potassium content. All right, now this is the data that we have here. All right, X1, X2, and X3 is given to you for 20 individuals. From previous studies, doctors had the conjecture that a healthy female at certain age group has her sweat data to be 4, 50, and 10. So we know that mu 0 under bar, this is 4, 50, and I think something is wrong today. I don't know why this is behaving so weirdly. But I've seen this happen in the past as well. Anyways, so you have 4, 50, and 10. And then to verify this, we need to perform a hypothesis test. So we really want to do H0, mu under bar is equal to mu under bar 0, and H alternate is mu under bar is not equal to mu under bar 0. Now to do hypothesis testing, we need two things. Let's go back. We need to have this X over bar under bar, and we need to have this matrix S. Okay, X over bar under bar is basically a vector containing mean of or sample average of every single quality characteristic. So you look at column X1, take the average of that. Look at column X2, take the average of that. Look at column X3, take the average of that. And you just put them in a vector, which is the vector right here. Again, my notation would be X over bar under bar. You can also use a bold notation, which I've done in the pretext that I've written here. Right, so now once you have the average vector, sample average vector, now next thing is to compute the sample covariance vector, sample covariance matrix, which is the matrix S. Now this is a slightly bit more time consuming step, but really what we're doing is that across the diagonal, these elements, actually, let me use a different highlighting. So the diagonal elements, these are just the sample variances. So look at X1, look at X2, look at X3, compute their variances, sample variances, and that's your diagonal, all right? And then any other value, for example, this one, this is S1, 2, this is the sample covariance between X1 and X2. And then you will use the formula that we had discussed before. Again, you don't have to compute this for the exam. You can just, I will provide you these numbers for you. Okay, now once you have everything, let's compute our T statistic first. So step number 1 is T statistic or T square statistic, which is equal to M is 20 times X over bar under bar, which is 4.640, 45.400, and then the last one was 9.965 minus mu 0. Mu 0 is 450 and 10. Take the transpose of this, and then you need to take the inverse of the S matrix, right? I've already taken the inverse of the S matrix, so I'm going to just give you that. Please do verify. 0.586, negative 0.022, 0.258, negative 0.022, 0.006, negative 0.002, 0.258, negative 0.002, and you have 0.402. So that's your S inverse. And then finally you have, again, 44.640, 45.400, 9.965 minus 450, 10, and then that's all. Now, once you compute this giant matrix computation, you will get 9.74. Second step is to compute T square critical which is your alpha at some alpha value. Let's take alpha as 0.05 in this case. So with that value of alpha, your t-square critical is 19 divided by 17 times 3, f of 0.005, your m is 3, your p is 3, m minus p is 17, and then this gives you 10.72. And so number 3, you can say that t square is less than t square critical at alpha. So you fail to reject null hypothesis. And that's your multivariate hypothesis testing. All right, now once you're done hypothesis testing, let's look at two more things. The first one is going to be a control chart where mean and variance are known. And then the second example is when mean and variance are not known. And this is probably the easiest part. When mean and variance are known, you will actually compute a t-square statistic. As I said earlier, anything that you do is called a t-square statistic. But now we compute t-square for every single sample, each sample k. Okay. T squared k is xk under bar minus mu 0 under bar transpose sigma 0 inverse xk under bar minus mu 0 under bar transpose. So you basically compute this for every single sample, and then your UCL is chi square alpha comma p, and then your LCL is 0. Okay, let's look at an example. So I have some data here on the right hand side, and mu 0 and sigma 0 are given to you. The first column is x1, the second column is x2. Now for every single sample, I have to compute a t-square statistic. Let's look at the first sample. First sample is x1 under bar, which is a vector. This is nothing but 2.0229, 5.7223. So I have x1 under bar. I can compute t1 squared. This is equal to 2.0229, 5.7223 minus 25. Take the transpose of this, and then you have your 1, 4, 1.5, 1.5. Take the inverse of this matrix, and then finally you have your 2.0229, 5.7223 minus 2, 5. And then if you compute this, you'll get 0.27. And similarly, you'll repeat this for T2, sample 2, sample 3, and so on and so forth. And once you've computed all the t-square statistic, you'll compute your UCL, which is your chi square alpha comma p. Alpha is, let's say, 0.05. P is 2. So you can compute chi square 0.05 comma 2. This is equal to 5.99. And that's pretty much it. That's all that you need for a multivariate control chart. Now, this is what you have here. Your UCL is 5.99. And now you can clearly see that this control chart, this t-square control chart that you have here, there is a shift somewhere at sample number 10, right? And that makes sense because when I created this data, I took in control process mean to be mu 0 equals to 2.5. And then out of control mean mu A was 4.8. And so you see this dramatic shift in the control chart. All right, very good. So now finally, what we will do here is we'll look at a scenario when mu0 and sigma0 are not known, they're unknown. Now, if they're unknown, we basically have to estimate them from data, okay? So to estimate mu0, for mu0, we're going to compute grand average vector. What is a grand average vector? Grand average vector is x double bar is grand average, and underbar represents that it's a vector. And this is nothing but grand average of x1, grand average of x2, and so on till grand average of xp. Okay. All right, very good. Now let's look at a little bit about how do you compute x1 double bar. Actually, let's just talk about xi double bar. That's probably easier. Xi double bar, this is equal to 1 over m xij, j equals to 1 to m. And then there is a bar here. And what is xij bar? Xij bar, this is equal to 1 over n summation of, actually, yeah, let's call it xik. That's probably better notation wise. Okay, let me write this one more time. This is equal to summation of k is equal to 1 to m. I want to use k to denote samples. So that's why I'm using this notation bar. And then xik bar is equal to 1 over n xi j k, which is, and the summation for j is equal to 1 over n. Now, again, you don't have to do these computations. What I'm trying to tell you is that for every single quality characteristic, let's say quality characteristic xi, you have, let's say I is your quality characteristic, right? So I can go from 1 to p. J is your, J is your number of samples. J is your number of, actually, number of observations, which is also the sample size, number of observations, which is the sample size, and that is always 1 through n, and then k is your number of samples. Okay. All right, good. Now in the exam or even in the assignment problems, I will give you this this grand average vector. So you don't actually have to compute them, but I'm showing you how I did those computations. Now you'll need one more thing. You will also need this vector, and again, I'll provide you this vector. This vector is basically x over bar under bar k. This is nothing but x1 k bar, x2 k bar, dot 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 up to x p k bar. This is just the average for every single sample, for every single quality characteristic, right? And this is what I'm going to call as sample average vector. Sample average vector. And then this, I'm going to call this as grand average vector. Right. And then the last thing that you need is sample covariance matrix, which I'm going to tell you. Sample covariance matrix is essentially S over bar. Again, I'll provide you this one, S11 bar, S12 bar, all the way up to S1P bar, S21 bar, S22 bar, up to S2P bar, SP1 bar, SP2 bar, up to SPP bar. That's how your this is the sample average covariance matrix. Let me write this down. Sample average covariance matrix. Right? And here your SJH, anything that you see here is basically 1 over m summation of k is equal to 1 to m SJHK. And then how do you compute S? Let me write this down, SJHK. You don't have to again compute this, but I'll give you the formula. This is summation of I is equal to 1 to n xijk minus xjk bar times xihk minus xhk bar. Again, you don't have to compute this. I will provide these numbers to you in the exam and also in the assignments. And let's actually do an example right now to understand how to use all of these in a problem. Before that, let's see how we can compute our t-square statistic first. So t-square statistic for every sample k, this is equal to n times x over bar under bar k minus x double bar under bar transpose S bar inverse x over bar under bar k minus x double bar under bar. We had seen all of these just a few minutes ago. X double bar under bar is right here. X over bar under bar k is also there. And then S bar is just on the previous slide. So you compute t square k for every sample. And then you have your UCL, which is equal to m minus 1 times. Now, all of a sudden, my pen thickness has changed. This is very surprising today. UCL is m minus 1 times n minus 1 times p divided by m times n minus 1 plus 1 minus p f of alpha p comma m times n minus 1 plus 1 minus p. Very good. So now we have a statistic. Let's look at a problem. Okay, so tensile strength and diameter of a textile fiber are two quality characteristics that are to be jointly controlled. The quality engineer has decided to use n equals to 10 and fiber specimens in each sample. And let's basically do a control chart for this. So you have your quality characteristic X as tensile strength, and then your diameter. Right? Now let's actually use this to see how we can use our formulas that we have studied just a few minutes ago. Okay, good. All right, and we also know that n is 10. And then if you look at the table on the right-hand side, you'll see that m is 20. You have a total of 20 samples, and then p is 2. All right, we start by defining, let's start by looking at t square 1, t square statistic for the first sample. This is going to be equal to n times x over bar under bar 1 minus x double bar under bar transpose S bar inverse x under bar over bar 1 minus x double bar under bar. So really, as you go from t1 square to t2 square to t3 square and so on, All that changes is the first quantity here, this one and this one. Everything else remains same. So let's actually see what X double bar under bar is and what S bar is. So in the problem here, X double bar under bar is at the bottom of the first two columns, the tensile strength and the diameter, which is equal to 115.59 and then 1.06. That's your X over bar under bar. And then your S bar is equal to, also given right here, is 1.23, 0.83, and 0.79, 0.79. Notational wise, what I would say here is that this S1 bar squared is same as S11 bar, and this is same as S22 bar, and this is already the notation of S12 that we have used. Okay, very good. Right now, let's look at, and then you will compute, the S bar inverse here. All right, now let's look at what X1 over bar under bar is. X1 over bar under bar is equal to these two numbers right here, which is 115.25 and 1.04. Right? So you plug everything in this formula here, and you'll get T1 square as 2.16. And then you'll compute your UCL. UCL is equal to m minus 1, which is 19, times n minus 1, which is 9, times p, which is 2, divided by m times n minus 1 plus 1 minus p, which you compute as 179. Then you have f alpha is 0.001, p is 2, 179, and if you compute this, you'll get 13.72. And that's all you have in control charts here. You similarly compute T1 squared, T2 squared, T3 squared, and so on and so forth, and just put them in a control chart, and then this is what you will get. You have your UCL here, and then you have the control chart. And you can check whether there's anything out of control, in control, and so on. Right, so practice this example for the exam. I'll give one more problem exam. I'll give a few more sample problems in the assignment. So make sure you practice that. Other than that, I'll stop here. Thank you so much.